Hello, everyone. Welcome to Colloquium. Hopefully, everyone is now sufficiently caffeinated. We are very lucky to have with us today Seyda Ipek, who is an assistant professor at Carleton University, to talk to us about matter, antimatter asymmetry. In other words, why we are all here. She did her undergrad at Bill Kent University, her master's in theoretical physics at Koch University, her PhD in particle theory at University of Washington, and then was a visiting junior research fellow at the University of Oxford in 2015. She then went on to do her postdoc #1 at Fermi National Laboratory from 2015 to 2017, and then won the University of California President's Postdoctoral Fellowship and did postdoc #2 at University of California, Irvine from 2018 to 2021. She has done a lot of teaching and outreach and has organized a couple of workshops, including Dark Matter Theory Confronts Reality and Summiting the Unknown. So without further ado, allow me to turn it over to Professor Ipek.
Thank you very much. Are we going to get the lights turned on, or are the lights going to be like this? Oh, okay, yeah, that's fine. Thanks for having me. Yes, so today I am going to talk about why we are here, why we all exist basically in the grand scheme of our universe. But before we get to how our existence works, let's start with how we got here, how we got to the point of this the year 13.6 billion in the existence of our universe. So we believe, and I don't think my let's see. What about this? Let's see. Yes, okay, perfect. Now it works. So our model for the start of our universe is that there was probably some big event like a Big Bang. And then after that Big Bang, there was a period of inflation. What inflation does is that it's an era of exponential expansion. The space-time is exponentially expanding. This is just a model of the beginning of our universe. We don't know if inflation actually happened or not. But why we like this inflationary model is that through this inflation, when a tiny bit of our space-time, our universe, started expanding exponentially in an explosive way, this era erased any inhomogeneities and bad stuff, basically, that we wouldn't want in our universe. So inflation happened, and it erased any asymmetries and inhomogeneities and anisotropies in the space-time fabric of our universe. But inflation ended at some point because our universe is not exponentially expanding anymore. We don't know how inflation started, why it started, how it evolved, and how it ended. But at some point, we think that it's ended. And then after inflation, everything that exists in the universe just was created by some mechanism. We have models for this, but we don't know if those models are correct or not yet. So this is the very beginning of our universe. And in many of our models, we believe that this happened at a very high energy scale or high temperature scale. So I will kind of like keep track of time at the bottom axis here, and at the top axis I will be measuring energy or temperature. I'm working in the units where the Bossman constant is equal to 1. So if you think about energy as kBT, energy and temperature will have the same units. Okay, so this is the very, very beginning of our universe, and as our universe continues to expand, and it does continue to expand after inflation as well, but as it expands, it also cools down. And then this, because of the temperature change, our universe actually goes through a few different phases. One of the important phases in the history of our universe, or there are many important eras in the very early universe when our universe was like a minute old, but some of them are more interesting to me than others. So I'm going to tell you my point of view. There are other interesting stuff that happened before this in the early universe, or that could have happened before this in the early universe. I'm just telling you what excites me, basically. One of the exciting stuff that happened in the early universe is that when the temperature was about 100 GeV or so, this is a very hot temperature. It is, I think it's about 10 to the 12 Kelvin. I forget exactly. But when the universe was about 100 GeV in temperature and about a nanosecond old, the mechanism that gives mass to standard model particles happened. So this happens because the Higgs field acquires a vacuum expectation value. This is when the Higgs boson becomes massive as well. And that is a sort of a transition, because before this temperature, all the particles that were created were actually massless. So if you think about it, the electron has mass now, but in the very, very early universe, we expect that electron was actually massless. It only becomes massive after this temperature. Now, this is our understanding of what happened in the early universe. This follows what we know from the standard model, basically, and what we expect from the standard model. We don't know yet this actually happened in the early universe or not. Maybe there was some new physics or new dynamics that, didn't allow for this process. We don't know, but this is what we expect from the standard model. And this is a transition. So if you remember from your thermodynamics class, when, for example, water boils, it changes from a liquid phase to a gaseous phase. And this is actually two different phases of matter, being massive and massless for, especially for the force carriers. Anyway, so this is one of the mysteries regarding the early universe cosmology. The question of, did this phase transition actually happen? And if it happened, what kind of phase transition was it? Was it a first order phase transition? Was it a second order phase transition? If it was a first order phase transition, it would be very interesting, because this transition could have produced gravitational waves. And could we see those gravitational waves at gravitational wave detectors? Which would be fascinating, because that would give us a way to probe the earliest nanosecond of the universe, basically, which would be fascinating. But this kind of phase transitions, cosmological phase transitions, are a very active area of particle physics research and high energy physics research. So after this era, the universe continues to grow and cool down. And at some point, our universe is as cold as about one MeV. And this is another interesting era. This is when the universe is about 1 second to about a minute old. This era is called Big Bang nucleosynthesis. The name Big Bang comes from, for historical reasons, it's not exactly related to the Big Bang itself, but the nucleosynthesis part is the relevant physics here. What happens when the universe is about 1 mega electron volt is that the protons and neutrons in the early universe, they start forming nuclei. If you think about it, 1 MeV is kind of the nuclear binding energy. The earliest elements, these are very light elements, like hydrogen is, of course, just 1 proton, but you can also produce deuterium, helium-3, helium-4, up to lithium-7, actually, and beryllium-7. So these are the very, very light, the lightest elements that were formed at this point in time, right? These are called primordial elements. Actually, almost all of the deuterium in the universe was formed at this point. Right? The hydrogen and helium you can also make in stars, but deuterium, all of the deuterium we have in our universe is pretty much from this era. And Big Bang nucleosynthesis also gives us the earliest observables in the universe. So what we know about the earliest times in our universe actually comes from this time, this era, Big Bang nucleosynthesis era. We can measure the abundances or densities of these primordial light nuclei. We can look at how much deuterium exists in our universe, or how much helium-4 that was formed in Big Bang nucleosynthesis, and that tells us a lot about our universe. And this is the earliest time that we can measure. So anything before this, actually, we have no idea what happened. All right, I want you to keep this in mind, that the stuff that we know about our universe comes from when the temperature was about NMeV or not. I told you that there could have been a phase transition at 100 GeV, but technically we do not know if our universe ever made it to 100 GeV. Maybe our universe was formed much colder than 100 GeV, and we wouldn't know that yet. As the universe continues to grow and cool down, another important observationally important era is the time when the electrons in the universe, they now can bind into the nuclei, and then they just form neutral atoms. So the two electrons bind into the deuterium nuclei or lithium or beryllium, what have you, and then the universe becomes electrically neutral in a way. I mean, it was also neutral because you had equal amounts of probably electrons and protons, but but the universe was ionized before this, and when electrons bind into nuclei, there is enough. The photons can now escape, and then those photons we observed as the cosmic microwave background photons. At this point, our universe was about 3,000 Kelvin old, and now those photons, they lost some of their energy due to redshift, and they're at 3 Kelvin. And this happened when our universe was 300,000 years. And of course, so this is another. So this picture here is basically what the photons would look like. This is the temperature map here. The red points are where photons are just a bit hotter, and the blue points are when the photons were just a bit colder. And you can look at the correlations between hot and cold points, and you can tell a lot about what is inside the universe at this time, actually, which is super interesting. But it's also just this picture tells us the structure or what the energy in the universe is made up of. And just by looking at the cosmic microwave background photons, we can tell that our universe is about 5% made up of what we call the standard model particles or baryonic particles. These are protons, neutrons, and electrons, and photons, and some neutrinos. But it's only 5% of our universe. The 25% of the energy density in the universe is made up of dark matter. This is the structure we call dark because it doesn't seem to interact too much with light, so it doesn't have any electromagnetic radiation. And it's very hard to see, but we can know its existence through its gravitational interactions. And there's also 70% of the universe is made up of what we call dark energy. Yes. Can it interact with it? We hope it does, because that's how we would like to detect it and discover it. So there are good reasons for why it should interact, because I mean, from my point of view, I work on dark matter as well. It was probably created from the same origin, same mechanism after inflation as the standard model. So there should be at least the same parent particle or what it was. It should have some it should couple the dark matter to standard model as well. As far as we know, they don't interact as much, and very little, because we haven't detected their interactions yet. We only observe dark matter through its gravitational interactions. It really does have a gravitational pull. It's why the stars in a galaxy are rotating a bit faster than we would have expected. So we know it exists. We know it interacts gravitationally. And we know that it doesn't interact electromagnetically, because it really does not seem to be radiating any photons. Yes.
You know if it gets affected by gravity?
Yes. Yeah, absolutely. Yeah, it does actually. It creates a lensing, basically. It can. Yes. Yes. The question was if dark matter gets affected by gravity as well, and yes, it does. Absolutely. And dark energy, we know even little. It exists, and it is responsible why our universe's expansion is accelerating, and we pretty much have no idea what it is. But we know that most of the universe is dark energy. All right, so this is the makeup of our universe. And really, dark matter, again, so dark matter is 25%. There's much more dark matter than there are electrons in the universe that we know. But actually, I'm going to tell you about this 5% of the universe today, because there's also, even though we understand the 5% quite well, there are still many things that we don't understand about even that 5%. And then the rest of the 95%, we know even littler. So there's a lot to discuss and a lot to study, actually. And then after this era, there's a lot more happening in the universe. Our universe is now about 13.8 billion years old, and it's made up of many galaxies, stars, planets, what have you. And our solar system is about 5 billion years old. And now our universe is quite cold. All right. So as I was saying, our universe, we know what's in our universe. It's the picture of our universe when it was about a few 100 million years old. The stuff you can see here are very new baby galaxies and stuff inside the galaxies. And you cannot see the intergalactic dust and stuff, but you can also pick that light up with X-ray telescopes. But what you don't see is the 95%, the dark energy and dark matter. And again, most of our universe is dark energy and dark matter. But even the 5% is very important. And there's a lot we know about the 5%, and there's a lot we don't know about the 5%. That 5% is called baryonic matter. And this is basically what makes us, what is inside us. We are all made up of atoms, of course, and the atoms are made up of protons, neutrons, and electrons. Okay, and there's some photons in the universe as well, but let's think about the protons and electrons. And protons and neutrons, they are individually inside protons and neutrons. There are even smaller things called quarks. So protons and neutrons are not elementary particles like electrons. The elementary particles inside protons are called quarks, and quarks are bound by gluons inside a proton. So when we say baryonic matter, we usually mean a collection of these elementary particles and larger particles in the universe. And baryon is a collective name for protons and neutrons. They're just larger particles that are made up of quarks and gluons. And I will use the term baryon a lot during this talk, so that's why I want to define it. And the elementary particles are their interactions, their existence and their interactions are described by what we call the standard model of particle physics. So the standard model takes these elementary particles in and then describes how they interact with each other. And elementary particles can be divided into or put into a sort of a table, like the periodic table, with respect to their groupings and how they are similar to each other. One group is called quarks. The quarks and leptons are fermions. Fermions have half integer spin. For the standard model, fermions have spin 1/2. Spin is an internal angular momentum quantum number for particles. A group of fermions called quarks interact via the strong nuclear force, and quarks are what is inside the proton and neutrons. Another group maybe we are more familiar with is the leptons, and leptons have electrons in it. So electron is what orbits around the proton in our atoms, of course. And then there are heavier leptons called muon and tau leptons. Muon and tau are exactly like the electron in terms of their quantum charges. They're just heavier. Muon is about 200 times heavier than the electron, and tau is 10 times heavier than the muon. And then there are these neutral leptons called neutrinos. At the bottom, you can see the nu e, nu mu, and nu tau. And these are, as in their name, they are neutral. They don't interact electromagnetically, but they interact via the weak nuclear force. And the forces in nature are described by elementary particles called force carriers or gauge bosons. And the force carriers are integer spin particles. And for the standard model, their spin is 1. The gamma is for photon, of course. Yes, of course, photon carries the electromagnetic force. We have G here, gluon, for the strong nuclear force. So the gluon is what is responsible for keeping the quarks inside the proton. And then we have the W and Z bosons, which are responsible for weak nuclear interactions. And weak nuclear interactions are the reason why we have nuclear decay and how our nuclear reactors work, for example. The central particle here is called the Higgs boson. It's also a boson. It's spin 0. It's one of a kind. It's a scalar particle, and it's the latest discovered particle in the standard model. It was discovered in 2012 at the Large Hadron Collider at CERN. And Higgs boson is an amazing particle. It's also responsible for why the massive particles in the standard model actually have mass. And as I told you, that mechanism that gave mass to the standard model particles could have been through a phase transition in the early universe, and that would be very interesting. So this is our understanding of the standard model particles. And of course, there is no gravity here. That's because we don't know how gravity fits in our quantum understanding of these particles. So we don't know how gravity is quantized, and we do not include it in our periodic table and our equations. Right? And these are very light particles, so that's kind of okay. Yes, so I already told you about the force of nature, and I put the gravity here because we don't know. It might have a quantum particle called the graviton, but we really do not know about gravity's quantum nature yet. We understand gravity very well classically. We just don't understand it at a quantum field theoretical level. And really, these standard model interactions are governed by relativistic equations. And I was thinking about how we get to the standard model interactions from basically Newton's first law. But what I want to say about this is that the standard model particles are very light things, and they are usually moving at the speed of light. And to describe their interactions, we use quantum field theory, which is a relativistic version of quantum mechanics, which is used for non-relativistic objects, but non-relativistic very small things. If you have relativistic large things, you use relativistic general relativity equations, right? But these equations, there's one important thing about this equation that I wanted to show here. This is specifically for fermions, actually. This is the Dirac equation. Right? It's a form of the Schrödinger equation for relativistic fermions. And what the Dirac equation actually predicts, and the Dirac equation is very important for the standard model as well. What the Dirac equation predicts is that it predicts both a fermion and an antifermion, so a particle and an antiparticle. So for example, for an electron, the Dirac equation will tell you that there should be a particle with the same mass with the opposite quantum charges. And this is actually what happens in nature. So for all standard model particles, well, the ones that this can happen, they're also antiparticles. This is really dictated by the equations that describe the standard model particles. This is also what we observe. For example, for electrons, we already discovered anti-electrons. We call them positrons. It has this exact same mass, just opposite quantum charges as the electron. You expect to have, for a muon, you expect to have an anti-muon. For a tau lepton, there will be an anti-tau lepton. For quarks, there will be anti-quarks. And really, this can even go further up. For example, 3 quarks come together to make a proton, and then 3 antiquarks will come together, bind through the same nuclear force to make an antiproton. And a proton and an electron, they bind together to make a hydrogen atom. An antiproton and positron will bind together to form an anti-hydrogen atom. And we can make anti-hydrogen atoms in the lab, and we do look for their properties, or we try to understand their properties to make sure that they actually do behave exactly like what the hydrogen atom would behave. So this is antimatter. It's expected from the standard model and it's been observed in nature as well. For all, this is I won't talk about it that much, but the only time this might fail is for neutrinos. Neutrinos are neutral particles, and we do not know if their antiparticles are distinct particles or not. There is a possibility that neutrinos are actually their own antiparticles, and that would be a new type of fermion that we haven't observed yet, which will be very interesting. There are experiments in Canada and in Europe that are trying to figure out if neutrinos are their own antiparticles or not. Neutrinos are fascinating, and of the standard model particles, one of the least understood particles are the neutrinos. Right, so antimatter is very normal. I actually used to work at, as Miriam said, I used to work at Fermilab, which is a national accelerator laboratory in Illinois, USA. It's around Chicago, suburbs of Chicago. And Fermilab used to run a particle collider called the Tevatron. This is something like a Large Hadron Collider, but not as large. And Tevatron was an interesting machine. It actually collided protons and antiprotons. And it was running, when it was running, it was producing 10 to the 10 antiprotons per hour. It's not running anymore. It's been defunctioned after LHC turned on, because LHC is a much stronger machine and runs at larger energies. But when you collide protons and antiprotons, many interesting things happen, and then Fermilab looks for those. And Fermilab actually discovered several of the standard model particles. So this is just to say that we understand antimatter and we produce antimatter in our particle detectors, even at the Large Hadron Collider. A Large Hadron Collider is a proton-proton machine, so it collides protons and protons. But when you collide two proton beams, a lot of stuff will happen, and some of the particles, and you will produce a lot of standard model particles, and hopefully some undiscovered particles as well. But together with particles, you will also be producing antiparticles. So when I say particle, I'm usually referring to elementary particles like electrons and positrons. The stuff like protons and neutrons they can be also called particles, but remember that they are not elementary particles. There are more elementary structure in them. And when we say elementary particle, we mean that something that cannot be further broken down into smaller things. For example, proton, when you collide them, they will break into their constituents, which are quarks, but you cannot break quarks into smaller things. As far as we know, quarks and electrons and muons, they are really fundamentally structured particles. There's no inner structure inside them. They're fundamental particles, and they are point particles. So this is antimatter. I hope we are all disenchanted by antimatter and we don't think it's weird. What is weird is that there seems to be no antimatter around us. Because one thing we know from antimatter is that when matter and antimatter come close to each other, they will annihilate each other. You can only think about electron and positron. Electron has minus E charge. Positron has plus E charge. And they are, for all intents and purposes, the same particles, except their electromagnetic charges. And if you add minus E plus E, you will get 0. And this is a very crude model, but really it does happen like this. If an electron and positron come close by, it will turn into pure energy in the form of probably photons. And this happens for protons and antiprotons as well. If you just kind of bring them together, they will just combine via their whatever they interact with, and they will just go poof. This would happen with larger particles. If there was an anti-Seyda here, we would eventually attract each other and we will just hug and disappear. And this would happen if there was an anti-Earth, if there was an anti-solar system, anti-universe. We will come together and annihilate each other. This sounds a bit, okay, duh, but it actually tells us something, that if there were equal amounts of matter and antimatter in the universe, at some point, the universe was very small and they would have been very close to each other and they would have just turned into energy. Electrons would have just disappeared because they would have annihilated with positrons. Quarks would have annihilated with antiquarks. But obviously, we have quarks now because we have protons and electrons, right? So that means that at some point, there was no antimatter to annihilate with the matter in our universe. That is like the reason why we are here is that there was an matter-antimatter asymmetry. The asymmetry is that there is no antimatter, basically. Because if there was antimatter, there would have been no structure in the universe. There would be just pure energy. You couldn't have had electrons. You couldn't have had protons, which will later make atoms and stars and galaxies. Okay, so our existence, so why we are here, the answer is the matter-antimatter asymmetry of the universe. And this asymmetry can be measured at 2 different times in the history of our universe. One of those times is actually from this picture, the cosmic microwave background picture. So these photons, as I said, some of them are a bit lighter, some of them are a bit hotter, some of them are a bit colder. The number density of photons and the correlations between photons that are coming from different directions in the universe, it depends on the matter-antimatter asymmetry in the universe. Because again, when matter and antimatter come together, they will annihilate and they will turn into photons. So that matter-antimatter annihilation actually affects the photons we will observe later as the cosmic microwave background. And from the cosmic microwave background, we can measure a quantity called the baryon to photon ratio. And this number eta here is a very important quantity, especially for my research. It's the number density of baryons. Again, baryons are protons and neutrons. Number density of baryons minus number density of antibaryons over divided by the number density of photons. Sometimes you take the ratio with respect to the entropy density of the universe, but for all intents and purposes, the entropy density is very similar to the photon density, number density, because most of the contribution to the entropy in our universe comes from photons. Photons will always be relativistic, and they will always contribute to entropy. Yes. It's a density, so you don't need to think about the volume. This is why we like densities, actually, because the universe is always expanding. This is, you can think of a co-moving volume if you want to think about a number of number of something, or a total entropy, for example. But good question. You can calculate this. You mean observationally, or? Oh, so one of them is, again, the peaks and the relative positions of the correlations between the cosmic microwave photons is affected by this number. So you don't directly measure this number. It is actually derived from something. And the second place you get this number is the abundance of light nuclear element, light nuclei that were formed during the Big Bang nucleosynthesis. And is this the last slide? Oh, sorry, I took out that slide. But anyway, so the thing is, obviously the light nuclei, the first nuclei in the universe, were all made up of matter. So this number density, this baryon to photon ratio affects how much deuterium you will have at the end. For example, if you started with 10 billion quarks plus 10 billion antiquarks, those would have been all annihilated, and then you will have 0 hydrogen. But if you had 3 extra quarks, you can have 1 proton. So this number actually, yes, so this 10 to the minus 10, so it's a very small number, 6 times 10 to the minus 10. And that small number corresponds to an asymmetry of, again, like 1 in 10 billion or so. So if you have 10 billion quark-antiquark pairs, you actually want to have 1 extra quark, so that 1 extra quark will then produce a proton, later, basically. So this is again, it's a very, very small asymmetry, but if you have any asymmetry, the symmetric part annihilates, the symmetric part of the matter and antimatter annihilates, and then you just end up with the extra matter or extra particles. So that's what 10 to the minus 10 refers to, basically. And the annihilated part produces the photons. Okay. So yeah, so this is what we are trying to understand. Why was there that extra quark or extra proton, basically, in the early universe? And you need to produce this asymmetry before Big Bang nucleosynthesis, because again, the elements, the nuclei that were formed during Big Bang nucleosynthesis, which was when the universe is about a few seconds old, they are all from matter particles. So you definitely need to produce this asymmetry before Big Bang nucleosynthesis. And we also strongly believe that when inflation ended, the universe was in a symmetric phase, or at a situation where there would have been equal numbers of matter and antimatter. So between the universe's birth, or between the end of inflation, and before it was a second to a minute old, you really need to get rid of all the antimatter, and so that we will end up with matter particles. And to have such a universe, the particle physics model that needs to govern that universe, it has to satisfy 3 conditions. And these are called Sakharov conditions. Sakharov, the name comes from a great Russian physicist, Andrei Sakharov. Andrei Sakharov is a very interesting character, actually. I recommend you learn about him. He received the Nobel Peace Prize in 1975, not the physics prize, Nobel Peace Prize. He was actually one of the fathers of the Russian hydrogen bomb. But after at the end of the Second World War, after he witnessed what happened in Japan when the US bombed it with atomic bombs, he absolutely gave up all his war or weaponry efforts, and he dedicated his life to peace and anti-proliferation. He's actually he worked very hard to get US and Soviet Russia to sign anti-nuclear proliferation treaties. And he was exiled, He was imprisoned by KGB. And when he received the Nobel Prize, he actually wasn't allowed to leave the country, so he couldn't get his Nobel Prize. My advisor, Anne, she tells a story. They invited him for a baryogenesis workshop in the US, and he sent a telegram saying, I apologize, I cannot attend. I am told I am sick, because he was at the time in exile. Anyway, so Sakharov is an amazing physicist. He also did foundational research in our understanding of the matter asymmetry. So we know by his work that in order to create a universe that is asymmetric between particles and antiparticles, any physics that governs the interactions of these elementary particles has to satisfy these three conditions. One of the conditions is baryon number, or baryon minus antibaryon number, basically, cannot be a consort quantity. This is, I will explain a bit more detail what these mean. The second property is that charge and charge parity symmetries must be violated by these interactions, and that our universe has to be out of thermal equilibrium or out of thermodynamic equilibrium. What does these actually mean is that, so the first condition is baryon number violation, and baryon number, I mean net baryon number violation. Again, we believe that at the very beginning of the universe, right after inflation, the number of quarks and number of antiquarks were equal to each other. So if we were to write a net baryon asymmetry or net baryon number, defined as number density of baryons minus number density of antibaryons, or you can think of this number density of quarks minus number density of antiquarks. So at the very beginning, this net number was 0. And if it is a consort quantity, it will always stay 0, right? That's what conservation means. Something doesn't change in time. So we don't want this to be a consort quantity. We want this actually be we want this to be violated. That's what the particle physics terminology. So this net baryon number cannot be a consort quantity. So it cannot be a consort quantum charge. So that we will end up with net baryon asymmetry, basically, at some later time. So this is baryon number violation. And the charge and charge parity violations are a bit more subtle. We basically want our forces in nature, or the interactions between elementary particles, to differentiate between particles and antiparticles, actually. And how we define particles and antiparticles, I told you just the quantum charges of the particles and antiparticles, but there is not only the electromagnetic charges, but there's also another quantum property of fundamental particles that is important for baryon number violation, and that's handedness. So just like some of us are right-handed, some of us are left-handed, the elementary particles also carry an intrinsic handedness. We call this chirality, or sometimes helicity. So some particles are left-handed, some particles are right-handed. Some antiparticles are left-handed, some antiparticles are right-handed. So if they were spinning, some of them will spin clockwise, and some of them will spin anti-clockwise, counterclockwise, basically. So we start with the left-handed proton, and then we do a charge transformation. What the charge transformation does is that you take the quantum charge of a particle and then make it the negative or opposite of that quantum charge. So a left-handed proton turns into a left-handed antiproton. We change all the electromagnetic charges. And then a Pareto transformation. A Pareto transformation is a mirror transformation. You take a left-handed particle and turn it into a right-handed particle. So when you do a charge transformation, a left-handed proton turns into a left-handed antiproton. And if you do a Pareto transformation, a left-handed antiproton turns into a right-handed antiproton. So you basically want your physics to differentiate between left-handed protons and right-handed antiprotons. Okay, so this is one of the really important things that you need to satisfy so that you create a better antimatter asymmetry. You want the left-handed protons and right-handed antiprotons to behave differently under the same force. And the out of equilibrium condition is a bit even more subtler. So if you think about thermal equilibrium, like really think about chemistry. If you have a reaction that turns A plus B into some other molecules, maybe C plus D, if that reaction is if it is in thermal equilibrium or thermodynamic equilibrium, that means that the C and D particles come together and then form the A and B molecules. So anything that happens one way would happen the opposite way at the same rate in thermal equilibrium. That means you haven't gained anything. So if you start with a symmetric phase, if the universe is in thermal equilibrium, even though there might be some process that creates a baryon asymmetry, same process would probably erase that asymmetry and go back to the symmetric case as well. So in thermal equilibrium, really nothing interesting happens. You don't want to be in thermal equilibrium. You want to have a process that creates a baryon asymmetry so that we end up with this nice structure in the universe. But you don't want the reverse to happen. You don't want your antiparticles turning into particles again and then create with whatever that was in the universe. Okay, so these are the three Sakharov conditions. And of course, we also have a very nice model of particle physics, right? We had a standard model. We understand the standard model, and we know how the elementary particles in our universe interact via the standard model or explained by the standard model. So the next question we ask after having known the conditions to create a antimatter asymmetry is if the standard model can create such an asymmetry. So if are the Sakharov conditions actually obeyed by or satisfied by the standard model of particle physics? And some of them are actually most of them are. So the standard model is very interesting. It's actually at the Lagrangian level. So when you write it with pen and paper on your chalkboard, it actually does not violate baryon number. All the interactions come with a quark and an antiquark, or an electron and positron at the same time, so that the particle number is not violated. But at very high temperatures, it actually is by what is called a quantum anomaly. It's a bit of it's interesting to study and kind of hard to understand. But imagine our universe being in a potential that depends on the net baryon number of the universe. Okay, so our universe at 0 temperature sits in one of these minima, and the potential is actually like a cosine potential. So at 0 temperature, our universe is not changing its baryon number. Whatever baryon number we have, we are stuck with, because the only way to change from one minimum to the other minimum is by quantum tunneling. And quantum tunneling can happen, but it's very hard, especially if your potential is quite high. And this quantum tunneling rate actually goes like e to the minus 4 pi over alpha weak. And alpha weak is a small number. And this rate is about, this is the coupling constant that governs the weak interactions. This is about e to the minus 160. This is great because we do not want to change our baryon number now because it's not changing. We don't like see our stars going poof basically for no reason. So this is good. But at very high temperatures, the universe can be more energetic basically, or the stuff in the universe could be more energetic. And instead of tunneling, the universe could actually just kind of roll over this potential. And these kind of processes are called sphalerons. Sphaleron is a Greek word that means, I think, rolling. Just means rolling, I think. And so sphalerons, via these kind of processes, you can actually violate baryon number, or you can get a baryon asymmetry. So this is very interesting, and they do happen very efficiently in the early universe. And when I say early, at the temperature above 100 GeV or so. So this happens very fast, very efficiently in the symmetric phase, and when the standard model particles were massless. And its rates goes like t to the 4. Yes. Yeah.
How is it?
Yeah. So these sphalerons are quasi-particles. They are not stable particles, but what they can do is, for example, take 3 quarks and turn it into 6 quarks and 3 leptons, basically. So they allow for these kind of interactions. Very good. If you know about instantons, they are some sort of instantons. But anyway, yes. So, but the thing is, with the standard model in the early universe, baryon number was not a consort quantity actually. Okay. But this only happens at temperatures above 100 GeV or so. And also, the standard model is not symmetric under charge and charge parity transformations. And this is due to weak interactions again. The sphalerons are, they are there because of weak interactions, Also, the charge and charge parity symmetries are broken because of weak interactions too. If you have ever seen the standard model, if you have seen anything about the standard model, you might have seen its group structure, SU3 cross SU2 cross U1. These three groups basically describe the strong interactions, weak interactions, and electromagnetic interactions. The group SU2 has a subscript L, and L is for left-handed. So the weak interactions, they only see left-handed particles or right-handed antiparticles. They do not, right-handed particles do not interact via the weak interactions. They only interact via electromagnetic interactions. So for example, if you look at this side of the slide here, if you have a left-handed electron, it interacts with the weak interactions. If you do a charge transformation, you turn it into a left-handed positron, which does not interact via weak interactions. If you do a parity transformation, a right-handed electron, it does not interact via weak interactions. If you do this transformation successively, a left-handed electron interacts via weak interactions, and a right-handed positron also interacts via weak nuclear interactions. But it turns out, for reasons that are not clear theoretically, it turns out the interactions of right-handed positrons are a teeny tiny bit different than interactions of left-handed electrons. And this is CP violation because these two interactions are just a bit different. And it only happens in weak nuclear interactions. For the purposes of electromagnetic interactions and strong nuclear interactions, these two particles are pretty much the same. They're the same. But weak nuclear interactions see a small difference, but a difference nonetheless. So the charge parity is actually also violated in standard model interactions. And this the discovery of this both parity violation and charge parity violation in the weak interactions received Nobel Prizes separately. But for technical reasons, if you try to use this charge parity violation from the standard model, it turns out even though it's there, and it's not too small actually. We see it in our particle physics experiments. But for the intent of creating a matter-antimatter asymmetry, it just happens to be not enough. So the asymmetry we need in the universe is 10 to the minus 10, and the asymmetry you can get from the CP violation in the standard model is 10 to the minus 20. So it is 10 orders of magnitude smaller. So even though it exists, it's just not enough, not even close, basically. And the third condition of out of equilibrium, requiring some out of equilibrium process, is not satisfied at all in the standard model. So all the standard model interactions, even though they might not be too strong. And when we say out of equilibrium in the early universe, what we usually mean is that a process is slower than the expansion rate of the universe. So what you are competing with when you say something is in equilibrium or out of equilibrium is the expansion rate of the universe. Imagine you have a scattering process. You literally threw two quarks to each other, or a quark and an anti-quark. So they are moving towards each other, but at the same time, universe expands. So they are getting stretched, space-time is getting stretched out. It could be that this interaction is so strong that they still find each other and they annihilate. But it could also be that the universe is getting larger faster, that even though they are moving towards each other, they will not be able to find each other at all. So when you think about an interaction is that it's usually competing against the stretching of the space-time. So we compare rates of several processes in the standard model to the expansion rate of the space-time and decide if they are happening fast enough so that they will be in equilibrium, or if they cannot happen because the universe, the space-time expansion wins over, basically. And similar process happens for how we think about dark matter came to be as well, but that's another story. Anyway, so for the standard model, even the weakest interactions, the weak nuclear interactions, are actually happening fast enough in the early universe that they will always be in equilibrium. So even though the weak interactions, they might be violating baryon number, and they might be violating charge parity symmetries, but they might be producing an asymmetry, but they're in equilibrium, so they would be erasing that asymmetry as well. So in the out of thermal equilibrium conditions is not actually satisfied by standard model interactions. There's only one path that you could think of within the standard model to get out of equilibrium conditions, and that's through a phase transition, specifically a first order phase transition. If the phase transition I talked about, the electroweak phase transition, when the Higgs boson acquires a vacuum expectation value so that the standard model particles become massive, if that transition was happening through a first order phase transition, then that would have been perfect. that creates really nice out of equilibrium conditions. And you could have produced the barium asymmetry, even though you don't still have enough CP violation, which I will come back to. But the thing is, in order to have a first order reactor weak phase transition, the Higgs boson should have been light. So Higgs boson's mass is 125 GeV. And so that's about 125 times the proton's mass. That's too heavy. That means that the phase transition just turns into a second order phase transition, which is almost an equilibrium process. So the Higgs boson, unfortunately, even though it's an amazing particle, it kind of failed us on the phase transition part. And that's why, so that's already the second reason why the standard model is not enough to produce this asymmetry. So again, the standard model, even though it has large baryon number violation and a very efficient baryon number violation, and it has CP violation, the CP violation is not enough. It is order of magnitude too small. And also, it does not have an out of equilibrium process. There's really no possibility of an out of equilibrium process in the standard model that would create the asymmetry at the right time. Okay, so the standard model can definitely not explain the matter-antimatter asymmetry of the universe. It cannot create a universe that would have been asymmetric. What we can get from the standard model is, it would have been produced symmetrically, and then there might have been a teeny tiny 10 to the minus 20, 10 to the minus 30 asymmetry, but that's not enough to produce the structure we have in our universe. Yes. So this is where the inflation again comes in. So the reason why we like inflation is that it erases inhomogeneities. Because you need that because you want the universe to be causal, basically. But while the inflation is doing that, it stretches space-time so much that it dumps in a lot of entropy, basically. So even if you had very large asymmetry at the end of inflation, that would have been just gone away. So if you believe in inflation, yes. Yes. 5 minutes? Yeah. So if you believe in inflation, there's no way that you could start with an asymmetric universe, basically. Yeah, so this means that there needs to be some new physics, and I'm running out of time. But so new physics, when I mean new physics, is that you need some new particles or new interactions that could produce this asymmetry. And what you need from that new physics is that you needed to have some particle number violating interactions, or you can use the standard model of baryon number violation, that's fine as well. But you definitely need some extra source of CP violation, and you need some out of equilibrium process. The thing is, when you say that you need some extra CP violation, then the question becomes, oh, if there was some extra CP violation, why we haven't seen it in our experiments? Or you say that, oh, if there was some new particle, why we haven't discovered in our particle physics experiments? If there was some process that violates baryon asymmetry, why isn't it happening right now? So of course, when you're building a new physics model, you need to take all of these experimental non-observations into account, and it becomes harder and harder to satisfy all these conditions. Especially actually the CP violation becomes very hard. And there are many different types of new physics models. Some of these include, for example, new Higgs boson, so extra copies of the Higgs boson basically. And these extra copies of Higgs bosons usually gives you a first order phase transition, which is very interesting. But we haven't observed any extra Higgses yet. There also, you can combine this question with another question in the standard model, which is why the neutrinos are massive. That's the whole other talk, basically, and another part of my research program. But while you are explaining why the neutrino particles are massive, you can actually produce an asymmetry through new particles called right-handed neutrinos. And these types of models are usually called leptogenesis models. And also another way to produce an asymmetry is you say that there's this other problem in our universe, dark matter. We don't know why dark matter is there, or we don't know what dark matter is. Let me push the problem to the dark sector. Let's say that an asymmetry is produced in the dark sector, and then somehow it gets translated into a proton asymmetry. These are called asymmetric dark matter models, which are also very interesting. And also they try to explain what the nature of dark matter is as well. And one type of model that I worked on actually was on what are called particle-antiparticle oscillations. This is a phenomena actually observed in the standard model. There are these bound states of quarks and antiquarks called mesons, and neutral mesons can oscillate into their own antiparticles. For example, a B meson oscillates turns into a B bar meson. A K meson oscillates into a K bar meson. And this is actually a very quantum mechanical process. This happens because what we call the interaction eigenstate is not the same as the eigenstate of the Hamiltonian. And we know that the eigenstates of the Hamiltonian, we find the eigenstate of the Hamiltonian because that's how particles propagate in time, right? So if you are not in an eigenstate of the Hamiltonian, you will evolve in time. You will turn into another, a mixture of eigenstates of the Hamiltonian. Okay, so it turns out for mesons, the way that you produce them are not the propagation eigenstates. So you can produce a B meson, but as it propagates, it will turn into a combination of B and B bar, and that combination will be an eigenstate of the, or will not be an eigenstate of the Hamiltonian either. But anyway, this is a very quantum mechanical process. I actually do ask this question in my quantum mechanics class, and especially in my quantum mechanics exams. And you can calculate this probability. We call this an oscillation probability. What's the probability of you will start with a B particle, and at a later time, you will end up as a B bar particle. And it happens the same way if you start in a spin up state, but then you have a Hamiltonian that mixes spin up and down, and then you will evolve into a spin down state, for example, later. So there's a hypothetical particle, elementary particle, which can do this as well. You start with all particles, and at a later time, you will maybe turn into all antiparticles or a mixture of particles and antiparticles. And if there's CP violation in this system, it turns out the mixture that you turn into will be antisymmetric later. Even though you start with a symmetric case, it might be a bit easier for antiparticles to turn into particles than particles to turn into antiparticles. So you might end up with an asymmetric final state, which is super fun, and it is also very hard to calculate, especially in the early universe. You need to solve what are called Bossman equations, and you need to solve the Bossman equations in an expanding universe, including many interactions that these particles could be going under. But at the end, you can actually produce this asymmetry with certain particles whose mass is very comparable to the Higgs boson mass, and who will definitely couple to protons, which means that you have a hope that you will be able to find them at a particle collider. So this is basically a new scenario, or the new mechanism to produce the baryon, the antimatter asymmetry of our universe, which is fun, and it predicts again new particles, not new forces, but a new type of elementary particle. And I will end here. Sorry, I might have taken too long, but I would like to thank my group. These are my current and past graduate students, and our funding agencies that allows me to study the universe.